Well, 35, I've counted. I can't believe that in the course where you actually get a homework assignment that involves beer, there's still attrition in the class. I don't believe it. Anyway, we've bent over backwards for you guys. Where are the other 7? Okay, maybe they'll come in. Okay. Of these short pedagogical talks on basics of nuclear physics, nuclear technology, nuclear power, this one is really core. This is where everything we're going to talk about, most everything we're going to talk about in this class, nuclear energy, nuclear weapons, this is where it comes from, nuclear fission. Let me just make a little bit of an advertisement. We have a tremendous opportunity coming up this week. Normally, the nuclear engineering colloquium would have been today, 4 to 5, but we have a guest lecturer coming from MIT. He's a young superstar. This is Scott Kemp. He was a undergraduate at Barbara in physics, did his degree, PhD at the Woodrow Wilson School at Princeton, and he is a phenomenon in the whole area of nuclear security. He's a professor at MIT. He was only in his early 30s, and yet he was a critical advisor to Secretary Ernie Moniz and the whole U.S. team negotiating the Iran nuclear deal. So he was one of the core teams through the whole process. He himself was responsible for several sort of very out-of-the-box technical innovations that have been published on safeguards, sort of warhead accountability, and so forth. And he is coming to give us a talk. It's going to be at 10 a.m. down the hill in our building, Echeverry 3110. And we're arranging for him to talk with a number of faculty and students. He's going to be here a couple of days, primarily I think Wednesday, but I think he may come back and join us on Thursday. One of the articles that I have put in the e-courses, you don't have to read it now, but there will come a time, he's written a fantastic article on the role of centrifuge technology in nuclear proliferation. And it's in the Proceedings of the National Academy of Sciences, and it's in the B-courses folder. And sometimes later, I think it's probably just after the spring break, we're going to be talking about separation technology, and I will have you read that article. It's a fantastically researched article. And as I say, we're really looking forward to having you with us. Okay, quick review of lecture 3. Alpha decay. Nuclei, particularly heavy nuclei, are unstable with lifetimes typically from years to thousands, millions, billions of years to emit an alpha particle, tightly bound in the core nucleus, and become 2 protons, 2 neutrons later. When you look at the spectrum, the energy of the alphas coming out, they come out in very sharp lines. And we mention that, as I say, is that spectroscopy is the major tool for forensics. When even thousands of miles away, you want to do airborne collection, you can tell from effluents from plants or effluents from tests, even below ground tests where radioactive xenon and other things diffuse to the surface and very, very dilute quantities get into the upper atmosphere and start floating away thousands of miles. There's enough material there to be able to tell what happened. There we are. Beta decay, 3-body process. Effectively, one of the neutrons in a nucleus transmutes into a proton. So it changes, it stays the same atomic weight. 14 is 14, 206 is 206, whatever. But there is an electron that travels away. Due to this very elusive neutrino that shares the energy with it, you tend not to see sharp lines, but you see a smooth spectrum, the end point of which also is spectroscopically and forensically valuable to know. In gamma decay, This is where either after a nuclear reaction or after a beta decay, when the nucleus is in an excited state, it will go from one of the discrete excited states to lower discrete states. And again, modern detectors can look at these lines with a resolution of a few parts in 10 to the fourth. So now these precise energies, you can see one line or maybe two lines, see the energy, and you say, aha, that's cesium-137, or that's polonium-210, or that's carbon-12, or whatnot. These things, again, are forensically rich. If you have not gone to the website of the nuclear engineering department, Bibber and others have had up since the time of Fukushima a couple of sites. One is called Rat Watch and the other is called Kelp Watch, where as a public service and simply to give people information and to also to educate people on the fact that there is background radiation which occurs independent of any human activity. After Fukushima, there was, several days later, predictably, carried by the high-altitude winds coming across the Pacific, isotopes that we're seeing that were carried down by rainwater, got picked up by grass, and so forth. And you can see, you can go there and day by day look at a gamma spectrum of the local environment and see lines there which now are predominantly, overwhelmingly dominated by ordinary activity, natural radioactivity in the Bay Area. There's very little left of anything that's worth looking at. It wasn't even that great when it started. But that goes to show you, you can actually see for yourself a real-life example of how gamma spectrum can identify what's there, what it is, and how it got to be there probabilistically. We talked about the exponential decay law. Again, this is a statistical process. You're doing a little do-it-yourself problem at home. And half-life is the natural log of 2 divided by the decay constant. This is the thing, the graph that did not, the recalcitrant graph that refused to show up last time. I showed you carbon-14, 5,730 years. This is the decay of potassium-40 to argon-40 with 1.25 billion years. The highfalutin scientists nowadays, instead of putting Y or YR per year, they on an A and dig on it. So that's GAs, billions of years. And this is a chronometer that can be used that people just up Ridge Road, about a block and a half, the Berkeley Geochronology Center. Paul Rennie, who's a professor in the Earth and Planetary Sciences department here, has a laboratory, is a world expert on the use of the potassium chronometer to measure the ages of crustal fragments, fossils, all that kind of stuff in the millions to billions of years lifetime. So let's now get into the topic today of fission. Here's the cast of characters. Otto Hahn and Lisa Meitner, Fritz Strassmann, a colleague of Hahn, and Otto Frisch, who was a nephew of Lisa Meitner. And in the 1930s, the late 1930s, people had, after the discovery of the neutron in 1932 by Chadwick, people had begun to do bombardment of various foils and looking at transmutation from fast neutrons to slow neutrons, and looking for nuclear reactions. Now, this is an interesting gang here because these are not physicists, these are chemists. And I say that without any curl of the lip. They're very respectable scientists, and they're very capable scientists. They had begun to see evidence in 1938, and even going back some years before that, that after bombardment of uranium foils with neutrons, when you did a chemical analysis, you began to see nuclei which were very far removed from the mass 230 some odd region, 235, 238, two natural occurring isotopes of uranium. And you started seeing things right in the middle. You started seeing things like barium and strontium and krypton and so forth. And it was very easy for people to say, can't be right. Clearly, these are very tiny trace elements they were looking at, and they said, it's obviously contamination. But these, as I say, were very careful, very patient chemists. Meitner had at some point fled, she was Jewish, fled to Sweden and continued the collaboration by mail, by letters back and forth between Sweden and Germany. Finally, in December 19th, 1938, they came to the conclusion, Hahn and Strassman came to the conclusion that there was beyond a shadow of a doubt that they were seeing nuclei which could not be explained by any other way than the fact that this was somehow a product of neutron irradiation of the uranium foil. This was not a contamination. They had proven to themselves beyond any shadow of doubt. The problem with this, of course, nuclear reactions have been seen already, and even man-made nuclear reactions for a dozen years now, or so, maybe not 10 years or so. Problematically, they did not see a good mechanism by which a single neutron coming in could cleave the nucleus, or to, as they said, chip off or knock off a significant fraction, to the extent of even breaking the nucleus in half. And it was the implausibility of that which made them question that what they had been looking at was a fluke. Had they seen Z of +1 or Z of -1 or something in the neighborhood of uranium, they would have said, okay, that's we could make a plausible scenario for such a nuclear reaction, but they could not plausibly come up with an idea how it would happen. Meitner was the one who suggested, based on Bohr's idea of the liquid drop model of the nucleus, that in fact it was a process by which the nucleus began to pinch down, form a neck, and then the Coulomb repulsion, the electrostatic repulsion, would drive the two nuclei apart to very great energies. Interestingly, they published this. It was in Nachrichtenschaften in 22nd of December of that year, with 3 days later. The news came to the United States very rapidly. Rabi, Fermi, Anderson, and others picked this up, reproduced it by the end of January 25th of 1939. They had reproduced it in the basement of Koopman Hall, the physics building at Columbia. And interestingly, the announcement to the world outside the physics community was done by Edward Teller at George Washington University. And in the following day, I think it was January 26th, at Washington, D.C., at George Washington University, they made the announcement to the world, to the public, that they had seen this phenomenon. Interesting, coded to that, people had been thinking that such a thing might be possible. Experiments had been carried out here at Berkeley, at the Lawrence cyclotrons, unsuccessfully, and it was someone brought the news to a person you may have heard about, Louis Alvarez, a very famous physicist, Nobel laureate. He was kind of a Renaissance man. He did all kinds of incredible things in every aspect of science, particularly particle physics, nuclear physics, whatnot. His son, Walter Anderson, I think, may still be an active faculty member. The father and the son came up with the theory that what killed the dinosaurs were these periodic extinctions every 26 million years due to a sister star in a binary elliptical orbit with the Earth slinging a bunch of stuff from the Earth cloud at the Earth, and these cometary impacts would have wiped out all life on Earth due to sort of just due to the atmosphere being enveloped, shutting off all sunlight and killing vegetation and killing all higher life forms for a period of several years. So, very prolific scientist. He was a graduate student at the time. He was getting a haircut down on Shattuck Avenue. Somebody came in and said, "Did you hear the news? Hahn and Strassman have published the discovery of nuclear fission. And apparently, they were so excited, he leapt out of the chair, and maybe, I don't know, maybe his head was shaved or something like this. They ran up the hill. I hope they paid the barber eventually. They ran up to the cyclotron, and within a matter of a day, they had set up the experiment and successfully reproduced it. And everyone was kind of going like, we missed it, we were screwed. But that was the beginning of something quite momentous. So what they had seen was due to the neutron bombardment of a natural uranium foil. They were seeing unequivocally byproducts in the mid-mass range here, barium and krypton, at the fission products from Z of 30 to 62, or remember this is the Z of this nucleus is 92 protons. And this is what Meitner had in mind. She was one who kind of solved the quandary and said, look, what happens, although this seems to be a very gentle process of a uranium neutron going to the uranium nucleus, it is really already quite unstable as it is, and this just gives it enough energy such that it becomes energetically favorable to begin to deform, pinch off like this, and then due to the immense electrostatic repulsion, then you get the propulsion of these two fission fragments going away like this. And importantly, the emission of some prompt number of neutrons that might be 0, 1, 2, 3, 4 per event. But typically, you're going to see about 2 and 2 or 2.5 neutrons per event, 2 to 3 neutrons event, which are emitted. And I think you can see where this is going. If one neutron can cause a fission like this, several neutrons in solid density uranium being emitted could give rise to the fission of several more, and then you get this exponential chain reaction. We'll talk a little bit later about the difference between fast and slow neutrons, but that's a story for a different day. This is something you've seen before. In fact, let me blow this up. That's the blow up here, just showing you the critical 1 MeV per nucleon around about an average of 8. Iron nuclei in the iron region are the most tightly bound per nucleon in the world. And the gain all comes from the fact that here you're looking at in the 230 range, about 7.6 MeV binding per nucleon. If I break that nucleus into 2 pieces, I still have the same number of nucleons. However, 2 nuclei at half the mass each, those nuclei have a binding of about 8.5, 8.6. So you're gaining approximately an MeV per nucleon, and that's where the 200 comes from. So you can say, well, where does that energy really show up? Most of it is the kinetic energy of the fragments. These are very large, lumbering nuclei that in solid matter will slow down and deposit all their energy, and that becomes heat. And that's about 170 MeV. So about 170 out of 200 is simply the kinetic energy of the fragments. You have a few, 2 to 3 per event. Again, that's a statistical event to event. Neutrons emitted, they carry away about 5 MeV. So these are what we call fast neutrons. They're carrying more than an MeV each of kinetic energy. You see prompt gamma rays emitted, then you see gamma rays emitted from the fission products themselves, and then some bigger particles and neutrinos, which are not useful. You can say, well, where on earth did those things come from? So here's a little quiz for you. So here's the chart of nuclei, which you've now become good friends with. You all know how to navigate around. You can go to the NNDC and have all kinds of fun looking around, looking at all kinds of bizarre properties, arcane properties of any one of these thousands of nucleons. There's our friend uranium-238. So 230, we'll talk about 235 in just a minute. They're all up here, all your fissionable nuclei are up here. What's the first thing you notice about this chart up here? So there's uranium. And I'm going to break this, for the time being, let's just say we're going to break it into 2 equal parts. What do you notice about that? The chart. Let's look at one of the non-scientists here. It's an interesting, not quite subtle. It's quite obvious when you look at it carefully enough.
There's a strange, very unstable section between.
That's true. That's true. And that's after you go above what's called a magic nucleus lead 208 out here. These nuclei out here actually tend to be slightly prolate, they're not spherical. But take a look at this region here. What do you notice about it? It's a little bit soft.
That at a certain point you need more neutrons for.
Yes, it's actually not a straight line. Not only is it neutron rich, it's actually bent. So let me schematize this a little bit. If you look at this thing called the valley of stability, I'm exaggerating that. Here's hydrogen down here, and here's uranium up here. I've exaggerated it. It's a little bit boomerang shaped. So what happens if I were to just split a uranium into 2 exactly equal nuclei? Where would that be? And you can look over here if you wish. Yes, but where would that be, including dividing the neutrons as well? The leading question is, this thing is not straight, it's actually curved, a little bit boomerang shaped. Where does it fall?
And the fission fragments would also be unstable because they have too many neutrons.
If I were just naively to divide this in half, they're actually on what I call the eastern slope of the valley of stability. So it doesn't. The black line here are nuclei which are absolutely stable. If I break the nucleus into 2 pieces, what happens is they're actually here. Now, as we're going to see in just a second, they tend not to break symmetrically, they tend to break asymmetrically. But either way, if I do a cross-cut here, and you see this is your homework, plot this, you tend to see, as a function of z for constant mass, you're basically landing on the eastern slope of the valley, and the nuclei ski down to the valley. And they ski down to the valley by beta decays. Because as we mentioned, whenever you have the possibility, unless something else prevents it, every time you have an initial system possible go to a more tightly bound system, a lighter system, it's going to happen. The bigger the difference, the faster, the smaller the difference, the slower. And so what you get is, and this is very strange, I don't want to get into the physics of this, oddly, nuclei tend not to break up into 2 pieces that are 118 each. That's Emily calculated for us. They tend to be a little bit asymmetric. That's something that we don't need to bother ourselves with. But typically, you'll find something around mass 140, and you'll find something about mass 95, like that. But since you're here, these things are landing on the side of the mountain on the valley, they decay. And now look, you go from things which are very unstable, 14 seconds, the next one 64 seconds, 13 days, 40 hours, and then serious stable. Here's strontium 94, 75 seconds, 19 minutes, down to zirconium 94, which is stable like that. So that's where those beta particles come from. It's after the fission, literally seconds later, these things begin to beta decay down, to ski down, as you should think of it, as skiing down to the valley of stability. This is what causes the long-term remnant heat in spent nuclear fuel. And the fact that spent nuclear fuel is highly radioactive. It's not when you turn off the reactor, everything becomes cold and safe. It remains hot, physically hot for a long time, and radioactive is the difference. What are the two isotopes in which one can readily make a nuclear reactor or weapon? This is very important. The US made both of these things, and they used one of each. The only two, as Professor Knox said, the only two nuclear weapons that were used in anger in history, human history so far, and let's just say hopefully ever used in human history. Uranium-235, and it turns out uranium-235, natural uranium that you dredge out of the Earth, is very abundant. Do you know how much of the Earth's crust is uranium and thorium?
Like a part per million?
Yeah, that's a lot. It's 1 or 2 parts per million of uranium and a few parts per million of thorium. Both of them are usable from an energy point of view. A lot of people who are scared of radioactivity and activists, they'll take a Geiger counter and they'll go to the beach and say, look at this, it's counting. You guys lied to me, there's radioactivity here. Yeah, and it's been there for billions of years, long before the evolution of human beings. We had nothing to do with it. And uranium has its own 4.5 billion year half-life within an alpha particle, and all of a sudden more alpha particles, gammas, betas, all the way down to lead. Uranium and thorium are naturally radioactive, and every rock, every cinder block in a building, every piece of beach sand has got this stuff in it, and potassium is all over the place as well. So there's not lots of natural radioactivity. Uranium has 2 isotopes, 235 and 238. Happily, for the good of mankind, the part that's fissionable when you drift in slow neutrons is the minority component, uranium-235, which is less than 1%, 0.7% of that is the fissionable component upon neutron bombardment. God knows what we would have done to ourselves if it had been the other one. The world would have been a mess. You know, I mean, we would have killed one another completely if every country could have made a weapon using natural uranium without separation. The separation is really, really, really hard to do, and that has been a barrier to preventing a lot of unsophisticated states, non-technically sophisticated states from making nuclear weapons. Now, it turns out, even today, that's kind of child's play. Unless you watch people very carefully, they can do that too. We'll talk later on about 4 ways of separating it. The United States, during the war, actually used what's called the electromagnetic separation. It was something that was dubbed by Ernest Lawrence and his friends as the Cal-neutron. Cal Berkeley. If you going down University Avenue, you look at the laboratory, you see that beautiful old dome where the advanced light source is. The building was saved for historical preservation reasons. It's a very historic building. They used to have a thing in there called 184-inch cyclotron. And they used the fact that 2 chemically identical elements, so 2 elements of the same charge, but at different masses, follow different radii, and you can separate them by their paths, by their radii. That was called electromagnetic separation. And they built up a big plant in Oak Ridge, Tennessee. We used gaseous diffusion, and those plants were in Hanford, Michael?
Yes.
Hanford. Okay. More recently, the centrifuge has taken over, and laser isotope separation. Actually, the patent belongs to an Israeli in many countries. Well, that's a very sophisticated way of separating. Plutonium is a different matter. Plutonium does not occur naturally, but if you run a uranium reactor that has any uranium-238 in it, most reactors you're not using 100% 235, you're using a few percent 235 and 97%, 95% 238. The 238 that gobbles up some of the neutrons coming by becomes uranium-239. It beta decays into Neptunium-235, and then beta decays to plutonium-239. 239, and now we've got a fantastically fissionable nucleus. This is problematic from other reasons. This is easily chemically separated, but again, you have to play with fuel wads, which are very highly radioactive, and you need a little bit of care and sophistication to be able to do this and to separate out the plutonium. But this is it's a different chemical element than uranium, and therefore it's really, this is a chemical process by which you can separate it. So I'm going to have an expert here. Jen Bailey from Colorado School of Mines is going to, nuclear chemist, will talk to us on April the 3rd about plutonium separation. Both fission and uncaptured slow neutrons. Lots of things fission if you hit them hard enough with a fast neutron. The important thing is here, these things will fission upon absorption of slow neutrons, in fact, preferentially. Fission products, we talked about. This is interesting. Let me go back. What happens? There's vanishing geograph. I know how to fix that. We'll use the PDF. All right. You saw it before, it vanished. Every time nucleus fissions, almost never does it happen the same way. It can split up any ways that the neutrons, neutron 1 plus neutron 2 equals the original neutron, proton, number of protons in the first, number of protons in the second equals the original nucleus. So what happens is when you split the uranium here, you might get one over here and one down here, or here and here. Or here, this will be exceptionally neutron-rich. This partner will be exceptionally neutron-light. So the number of combinations of the way this thing is split up is literally in the thousands. But when we talk about spent fuel being highly radioactive, you know, the fuel problem, the disposal problem, there's a few of these guys which are particularly bad actors, and you've heard of them. Cesium-137 is a very common fission product. Strontium is another one. When I was a kid, everyone was reading in the newspaper that strontium from the above-ground nuclear testing was getting into our food supply and was going to make our teeth go bad, and other things, get into your bones, give you cancer, whatnot. Iodine, many isotopes of iodine and xenon. This is the interesting thing. When you think about it, what are the one things you worry about in terms of radioactivity? The ones that are very long-lived, you don't have to worry about because they never decay. The ones that are short-lived, you don't worry about them either, because you can wait them out. Anything that you can wait out 10 or 20 half-lives is gone. So if the thing has a half-life of a few hours or a few days or even a month, a few years from now, it's gone. The ones in the middle that are too long-lived that you can wait them out, but short enough lived, remember, the number that decay is the number you got times the decay constant and the interval of time that you're looking, maybe 1 second. And that thing is 1 over, with some constant, 1 over the half-life, okay? The shorter the half-life here, the more they're going off every second. So these things that are 30 years half-life are really bad actors. You can't wait them out. In fact, you know, you can, because that's, 2 half-lives is already 2 or 3 half-lives of a human life there, so the whole issue of how you do long-term storage and get these things down to negligible amounts is a big issue. But they're short enough that these things are hotter than a pistol. In fact, when if you take something about the size of a sugar cube from a spent fuel rod, and I put it at the end of the room over there, I would get a lethal dose in 1 second, less than a second. It's that hot. Peter Hostman, who many of you know, he's an assistant professor in our department, the material scientist studies the degradation of steels and other things that have been irradiated in nuclear reactors. But he had a brilliant idea as a postdoc. He revolutionized the world of nuclear materials. He said, okay, maybe this much will kill you, but if you give me something that's a few microns on a side, that will have so little radiation in it, it can eat it. But he can study the thing nanomechanically. He goes to Stanley Hall, and they can do these fancy things with atomic probes and whatnot, and look at tensile strengths, but not measuring big pieces of steel, but measuring little pieces of steel. He gets the same number. So he's actually made studying highly irradiated steels and other stuff safe for any nuclear researcher to use. By the way, there's another database other than the NMDC. This one's from the International Atomic Energy Agency, the IAEA, and there's their website. And I'm just showing you A equals to 137. Now, the Europeans tend to be very contrary. I don't know, I think they did this just to annoy us. The neutron-rich side is over here, and the proton-rich side is over there. But this is probably the most perfect parabola you will find when you make a cut through the chart of the nuclides. And here you can see if you form a fission product, which is tin-137, that lasts 190 milliseconds, a fifth of a second, it beta decays to antimony, 137, it lasts almost half a second, 130 milliseconds. It beta decays to tellurium, 137, it lasts 2.5 seconds. It beta decays to iodine, 137, it lasts 25 seconds. Xenon, 3.8 minutes. And then here it comes to cesium, which is 30.8 years. It's only one nucleus, one proton away from the valley of stability. This one's absolutely stable. But this thing has this annoying property that has a Q value of 1.2 MeV. It's a lot of energy it gives off, and it's hotter than a pistol. It has a short enough half-life to give you a very high decay rate, but long enough that it's problematic in terms of you're not being able to wait the thing out. Let's watch one of these things and we'll quit. Which is the better one? These are not great, but they're okay. Let's see if we can fit this into it. Yes. You will like that. This was better. This wasn't great.
Educator.com. Get help in general and AP physics with video lessons and tons of examples. Learn everything.
In this video, we're going to talk about nuclear fission. Unstable radioactive nuclei, which occur naturally, sometimes emit strong radiation, especially in isotopes of uranium like uranium-238 or uranium-135. The disintegration converts the uranium isotope into stable lead, and in the process emits energy in the range of 1 to 5 mega-electron volts. That's 1 to 5 million electron volts, and even higher amounts of energy can be released by breaking unstable nuclei into even more parts. In 1939, a German scientist named Otto Hahn discovered that breaking up the nucleus of uranium-235 into 2 parts emits 200 million times the energy of the neutron which triggered it. He, along with his 2 colleagues, Lisa Meitner and Fritz Strassmann, found that when the nucleus of uranium-235 is bombarded with neutrons, it will absorb one of the neutrons. This results in an unstable compound nucleus, and the nucleus breaks into 2 equal parts. This process is referred to as nuclear fission. So, a process in which heavy nuclei are bombarded with neutrons and split into two equal masses, releasing enormous amounts of energy, is called nuclear fission. In the process, uranium-235 initially absorbs a slow-moving neutron, thus forming a highly unstable compound nucleus, uranium-236. This is what triggers the nuclear reaction. During the process of fission, uranium-236 splits into two product nuclei, which are barium-141 and krypton-92. You should notice that a barium atom has 56 protons and a krypton atom has 36 protons, which add up to the uranium atom's 92 protons. The unstable uranium-236 nucleus also releases 3 neutrons in the process. This happens because barium-141 has 141 neutrons, and krypton-92 has 92 neutrons, adding up to a total of 233 neutrons. To balance the equation, uranium-236 must emit 3 more neutrons. The chemical equation of the nuclear fission reaction taking place can be represented by this equation. So as you can see from the equation, 1 neutron combines with uranium-235, forming an unstable compound nucleus, uranium-236. This unstable nucleus splits into 2 stable nuclei, barium-141 and krypton-92. In addition to these 2 nuclei, 3 neutrons are also emitted, as well as a high amount of energy, denoted in the equation by Q. Since uranium-236 emits 3 neutrons in the reaction, these neutrons can be absorbed by other uranium-235 nuclei, resulting in a chain reaction. This leads to exponentially high amounts of energy being released by a single reaction. So, in this video, we covered that nuclear fission reactions result in massive amounts of energy being released. Now, these nuclear reactions are most well known for the part they play in nuclear fusion, but they are also an essential part of nuclear reactors, which have the capability to provide mass amounts of energy with relatively low cost. But that's a different topic altogether.
Actually, that was not just, the other one was better. Real quick, you should see the other, it's another 5 minutes or so. For the homework I'm going to give you this week, for the first time, I'm actually going to have you calculate these things we talked about, Q values. You go to the chart of the nuclei, I give you a reaction, you look up the mass excesses, you calculate the difference, and you tell me, was the thing exothermic or endothermic? Okay. It's going to be real simple, but for the first time, you'll actually do the math yourself, and I'm going to have you calculate some values. I'm finished. There's questions. Is that mystifying for anybody? Or are we all hanging in there? Looks good. Good.
Okay, I have about 45 minutes of material to go through, so maybe we'll take a short break and come back, and then I'll just go through it without a break.